Thank you, subscribers, for liking my videos. And I owe a thank you to all of you for all your support. Otherwise, this wouldn't have been possible from my side. And keeping on with the 11th standard GOC topics. The next topic I had explained in my last video, how compounds are named with its various rules. So now in this video, of course, I would be introducing the functional groups, and the functional group has already been introduced in my last few videos, which I could share the link in this video also. So you need to know functional groups, and then only you'll understand the next topic, which is isomerism. So going on to isomerism, while 11th standard, everything, a lot of concepts of isomerism is required off and on and on and off in so many topics. So starting with isomerism, which is the topic for today's discussion. So first of all, let me tell you what do I mean by isomers. Isomers are compounds having the same formula but different structure. So their structure can differ, and the phenomena by which two or more compounds having the same formula but different structure exist is called isomerism. So if you see isomerism, it is divided into two types. You will have the structural isomers and the stereoisomers. In case you feel that you need to note down something, pause the video, and then you could go ahead making notes, and that would serve a really good purpose for you. It would be worth the learning. So starting with structural isomers, they can be divided into chain isomers, position isomers, and third one, functional isomers, metamers. The tautomers are classed in this, but tautomers are also existing with may be called a part of the structural isomers. So apply a bit of chili and salt and learn it. It will definitely help you in so many aspects. So the stereoisomers will be dealt with me later on. So going on to structural isomers, which is the topic of discussion. Now, say we go on to the first one, which is the chain isomers. I've told you that isomers are compounds which have the same formula but different structure. You will get these definitions in any of the standard books. So the definition is not so important. Understanding is very important. So let us go on to a carbon chain having 4 carbons. So it has 4 carbons. So obviously the name is normal butane. Let us draw an isomer, which is a chain isomer of normal butane. So chain isomer means the chain length is changed to a chain length from 4 to a chain length of 3. But remember, chain length means starting from the first carbon to the last carbon, the length of the chain consisting of 4 carbons. But if you see in the second compound, I have tried to change the chain length to 3, keeping in mind that the 4th carbon has to be inserted not in the terminals, but in the center. If you put it in the terminals, it becomes the same compound, just that you're going up or you're going down. All right. So you put a carbon in the central carbon, and that is where you have reduced the chain length or changed the chain length from 4 to 3, and this is how this becomes an isomer. So if you put on the necessary amount of hydrogens, the IUPAC name of this compound, I will deal only with IUPAC, 2-methyl propane. But by the by, if you're interested in the common name, this is called isobutane. You will get a lot of information from my past video in case you've forgotten or you want to revive your memory. So let us go to this chain isomers. Yes, so these are the chain isomers because the chain lengths are different. So go on, creating different length of chains, and you get its chain isomers. Going on to the next isomer, which is position isomers. Position isomers are in reference to or with reference to a functionality. What do I mean by a functionality? The OH group represents an alcoholic group. So if I deal with this alcoholic group, or X, which is a halogen written by fluorine, chlorine, bromine, and iodine, then I have, say, a 3-carbon species where I put either the OH or the halogen, probably, you could go on changing it according to your necessity. So the OH group, because I have fixed it on terminal on the right, the numbering of the chain starts from here. So this is one of the position isomers. As you understand, change your position with respect to carbon, make the OH on carbon 2. So this OH, because it is on the second carbon, you have changed the position of the functionality. So naturally, compound A and B are position isomers of each other. You can do this with anything, any functionality. So you have chain isomers. You have position isomers, which is 1 and 2. So the first compound, I have made a lot of nomenclature videos. If you're interested in the nomenclature of these alcohols, I would definitely share the link so that you can check it out. So this first compound's IUPAC name is propan-1-ol. See, it's consisting of 3 carbons. So it's propan, you release the E, remove the E, and it's 1-ol, or simply you can write propanol. It's understood that the OH is on the first carbon. The next compound has the IUPAC name. Yes, if you have said propan-2-ol, give a pat on your back. You've done it right. Very good. So these are position isomers. So whenever we speak about position isomers, we think about changing the position of the functionality. Now, in the second compound, if you have numbered it either ways, from right to left or left to right, the second carbon, there is only one center. So it would be always propan-2-ol. But for the first compound, you need to be careful that the functionality, according to priority rules, is on the first carbon on the right, where the OH is to be given more priority compared to a carbon without any functional group. So this finishes the position isomers. We can take a lot of examples. Third compound, we'll go to functional isomers. In organic chemistry, we have a lot of functional groups where you have only one oxygen. It is an OH, which has one oxygen, or an ether, which has one oxygen. So whenever you try to think about functional isomers, you've got to think of the one oxygen or the two oxygen or any other functional group where you can do some interchanging, you can do some, permutation, combination, and stuffs like that. So let us go to a 2-carbon species containing an OH. So obviously this is an alcohol and it's ethanol. I have to change the functional group totally from alcohol to some other functional group which should contain one oxygen. And what are the ways I can do it? Put the oxygen on the center surrounded by the 2 carbons on 2 sides. Yes. So this is a new look for the compound where the oxygen comes in between the 2 carbons. So this is an ether. In case you're interested in the nomenclature of ethers, I have made an entire series of ethers of various types with a lot of common names and IUPAC names. I could share the link so that you can master it. If you go to the IUPAC name of this ether, it is called methoxymethane. So this is one of the functional isomers I have shown. Now there is often a problem, okay? And what is the problem? I'll tell you. A single oxygen is present in an aldehyde and also a ketone. So this single oxygen compounds, you have to be a little careful and count the total number of carbons and hydrogens which are present. And then you'll be able to reach a conclusion. So let me just explain to this. Get to this example. Say I have given you a formula like C3H6O. With this formula, you write 2 possible isomers. So you would start with 3 carbons. Okay, there is 1 oxygen. So probably I should go with an OH. So now you should look back and see how many total hydrogens are there in alcohol. Because 1 oxygen, there's a probability of an ether, an alcohol, an aldehyde, a ketone. So look back at the number of hydrogens and then you'll be able to fix it up. 3, 4, 5, 6, 7, 8. 8 hydrogens. I have not given you 8 hydrogens. So alcohol is slashed out. So thoda sa permutation, combination karna padega agar you don't know the general formula of compounds. But everything can be solved if you know the general formula of compounds. So obviously I'm going the easy way out. So yes, the next thought process is to focus on the ketone or the aldehyde. So if you can see the number of hydrogens, yes, it is ideally containing 3 carbons, 6 hydrogens, and 1 oxygen. So that means this 1 oxygen species can be an aldehyde, can be a ketone, or it can be an alcohol and an ether. So naturally, you got the stuff. So you know if it's ketone, which is your propanol. The other isomer of ketone is an aldehyde. So actually, you know, the isomers are in pairs. So either it's a propanal. So if you've got one isomer as propanal, you know the other isomer would be propanone. So an aldehyde and ketones are isomers in pairs, and alcohol and ether is in pairs, and a carboxylic acid and ester are functional isomers of each other in pairs. Got it? Good. Okay. Let's go move on to the next one. And the last one is metamers. Speaking about metamers, when we speak about metamers, we have an ether. I just taught you about an ether, which is you have. See, I cannot take 2 carbons and show the metamers. I have to take a minimum of 4 carbons and explain to you the metamers. So now I have given you an ether containing 4 carbons. And we are interested in writing the metamer of this, which is ethoxyethane. Ethoxyethane. So the metamer of ethoxyethane has to be another ether, but you have to deal with the number of carbons differently on either side of an oxygen. Yes. So both ethers are metamers of each other, where we have changed the carbon distribution on either side of oxygen. So the metamer of ethoxyethane is methoxypropane. Got it? So these are about metamers and structural isomers. Going on to the next type of isomerism, which is stereoisomers. So stereoisomers are subclassified into geometrical isomers and optical isomers. Here what happens is that in these stereoisomers, the structural formula, we do not deal with the structural formula at all. We deal with the stereochemistry. That means arrangement of the atoms in space. And this is everything about, you know, 3D conceptualization. So if you look at the geometrical isomers, which is cis-trans isomers, it is possible with a number of species, but my focus is on alkenes. So if I have an alkene, so I could have groups, similar groups, say Cl and Cl and H on the same side of the double bond. So if I have a double bond, this is above the plane and this is below the plane, right? This is above the plane and this is below the plane. So above the plane, I have similar groups. So this similarity calls on for cis. We have a German name for this, which is called the Zusammen. So the cis isomer is also called the Z or the Z isomer. And its other partner is this. I have not done any rotations. It is just that I have tried to do another variation, keeping the 2 chlorines, one above the plane, one below the plane, and that makes this compound trans because it is different. There are different groups above the plane, the hydrogen and the Cl, and there are different groups below the plane. That is trans. And this has a German term, which is entgegen. Entgegen, given the symbol E. So these are the geometrical isomers of a double bonded compound. Again, a number of variations, permutation, combinations are possible. But this is an introductory video. In the next, we can go to a number of variations. Going on to the next one, which is optical isomers. Optical isomers as optics, light. Yes. So we have something called plane polarized light. When is light plane polarized? So you have, say, light, monochromatic light, which if treated as a particle has vibrations, all right, in the XY plane, YZ plane, and ZX plane. If we pass it through a prism called a Nicol prism, then this light, which has vibrations in all the directions, gets plane polarized. Plane polarized means we have vibrations of light only in one plane. Say it is the XY plane. All right. So this plane polarized light, so this is a vibration of the particle of light in the XY plane. So say this light is plane polarized light. If we pass this light through a compound which is chiral or asymmetric, that means this carbon is attached to 4 different groups. Then there is a possibility that this light passes through the compound, the PPL passes through this compound, and this compound is optically active if it can rotate the plane of polarized light after light passes through it. So after PPL passes through this compound, there's a possibility that this light gets rotated. Say it starts vibrating in the XZ plane. So this special property of the compound to rotate plane polarized light makes this an optically active compound. Optically active means active to light in rotating the plane of the vibration. So this is what I mean by optically active. I'll take a typical example of it is, if you have 2-chlorobutane. So I have given you 4 carbons in this example, but the first carbon is not chiral, not asymmetric. It is achiral or symmetric. It contains 3 hydrogens. All right. If you see the second carbon, I will put an asterisk so that it is distinguished from the other carbons which are achiral. So the second carbon has 4 different groups. I'm circling the groups 1, 2, 3, and 4. Take this whole group and classify into the 4th group. So you have 1 group hydrogen, 1 group CH3, the 3rd group Cl, and the 4th group CH2, CH2. This makes this carbon, yes, you're right. It makes this carbon chiral. And if this compound is exposed to PPL, it will rotate PPL and it is proved optically active. So this optically active compound, which is my 2-chlorobutane, can be, that carbon, this compound, it's tetrahedral. So I'm just drawing a tetrahedral state of the species. So it will have its mirror image, which somehow looks like this. These are mirror images of each other. If this is a mirror kept in front of the compound, this is the image, this is the object. So object distance is equal to image distance roughly. So, if PPL is passed through this compound, it may rotate the PPL towards the right or clockwise, making it a dextro rotatory compound. And the other isomer, I'm passing PPL through this compound, it will rotate PPL towards the left or levo, making it a levorotatory compound, abbreviated as small l and small d. So these 2 compounds, both are optically active. They are non-superimposable mirror images of each other. You lift the compound from the plane of the screen of one and impose it on the other. When you superimpose it on the other, they are non-superimposable. So that makes them, yes, enantiomers of each other, enantiomers. So enantiomers are optically active isomers with non-superimposable mirror images of each other. So I hope this learning was of use, and do stay tuned in. A lot of fundamentals are coming with a lot of interesting things and interesting concepts. Do not forget to subscribe also so that you can get notified every time I build up on a new concept. So do keep watching, and thank you so much.